Our next speaker is Lia Medeiros, who is a postdoctoral fellow at the Institute for Advanced Study and an expert on both GRMHD and particular using black hole shadows to test as tests of gravity. And so she'll talk about some exciting new results from the Event Horizon Telescope on that. Okay, so please, Lia, go ahead.
Hi everyone, I'm Lia Medeiros, I'm at the IAS, and today I'm going to be telling you about a recent paper that just came out October 1st. It's an official paper from the EHT. The primary author is Dimitrios Psaltis, and what we were able to do in that paper is a first gravitational test beyond the first post-Newtonian order with the EHT. The simulation that you're seeing right now, I included this mostly just for fun. This is actually a free color image. It's results of GRMHD and radiative transfer simulations. And what you're seeing is what M87 might look like if you could see it at 3 millimeters, which is shown in red, 1.3 millimeters, which is shown in blue, and also 0.87 millimeters, which is shown in green. And what's interesting here is that hopefully you can see there's this very thin circle that's completely constant despite all of the other variability, and this is a white circle. And what's interesting about this is that it's bright at all three wavelengths. So this is the edge of the black hole shadow that I will be talking about a lot today. So before we begin, I wanted to start by clarifying what I think is a really important point to keep in mind. When we talk about testing gravity, it's really important to be very clear about what aspect of the theory of gravity you're actually testing. There are, of course, several different aspects that you can test in many different ways, especially using astrophysics. So what is the EHT actually sensitive to? So the EHT can't say anything really about the dynamical part of the theory. We're not sensitive to that at all. The only thing that we can really test is the metric for a black hole. So what we have is a almost perfectly static black hole with a very small mass around it relative to the total mass of the black hole. So we expect that the metric is going to be completely constant, and we're trying to test different aspects of this metric. You can contrast this with LIGO, for example. So with LIGO, they're sensitive to not only the metric of the black hole, but also sensitive to the dynamical part of the theory as well, since their black hole spacetimes are also changing as a function of time. And so it's important to keep in mind that there are essentially four possibilities. So it's possible that black holes are described by the Kerr solution to Einstein's equations, but that the dynamical part of the theory is not as predicted by GR. The opposite is also possible, that black holes are not Kerr, but that the dynamics of the theory are described by GR. And of course, it's also possible that both of them could be true or both of them could be wrong. So this is just something to kind of keep in mind as we're talking about this test of gravity. So what actually is the black hole shadow? There are many different ways to define this. I'm going to start with what I think is the most intuitive definition, which is essentially using an impact parameter. So what you're looking at here, this green circle, this is the event horizon of your black hole. The dashed black circle, this is the photon orbit of your black hole. And all of the red and blue lines over at the right, these are all photon trajectories. We're going to see how the trajectories of these photons are going to be affected by the presence of this black hole. So I'm going to go ahead and play that. And what you'll see is that all of the blue photons will fall into the black hole, all of the red photons will escape to infinity, and it's these blue photons that create what we call the black hole shadow. So it's really this absence of light, or you can think of it again as this impact parameter. And obviously the size of the black hole shadow, as is shown here, is significantly greater than the size of the event horizon. The event horizon isn't actually involved in this at all. So what I also wanted to point out is that if you follow the trajectory of this boundary blue photon right here, so it's right on the edge of photons that fall in and photons that escape, if you follow that trajectory, you'll see that at the back of the black hole here, it's essentially tangent to the photon orbit. And so what we're seeing when when we look at the black hole shadow is we're also seeing the lensed photon orbit. Either of these definitions is completely equivalent, but the photon orbit will be important when I explain what we did with the paper that was published last week. So the animation that I just showed you was what this would look like for a Schwarzschild black hole. But of course, we do expect that black holes in space will be spinning. And so how does the spin and the inclination angle of the observer actually affect the size and the shape of the black hole shadow? So the blue circle that you're seeing here, this is the edge of the black hole shadow. This is for a Schwarzschild black hole. But as I increase the spin of the black hole, you'll see that this shadow is going to move over to the right. So far, the size and the shape hasn't really changed that much, but when we get to really high spin, you will create this deformation that you see here. And so if you were to measure the radius for all possible Kerr black hole shadows, you'll find that they all are within the range of 4.8 GM over c squared and 5.2 GM over c squared. So that range is only about 4%. And so this is actually quite small. So there is a optimistic view of this or a pessimistic view of this. The pessimistic view of this is that if you wanted to use the size and the shape of the black hole shadow as is measured by the EHT to constrain the spin of the black hole, that would be really hard because 4% is a very, very small range, especially relative to the EHT errors. However, the optimistic view of this is that if instead you wanted to use the measured size and shape of the black hole shadow to tell whether or not black holes are consistent with Kerr, then this is really great because it essentially means that you don't have any free parameters and the black hole shadow only depends on the mass of the black hole and of course the distance between you and the black hole as well. And if you're interested in trying to understand why the black hole shadow doesn't seem to depend on the spin, what happens is that as you increase the spin of the black hole, you're increasing the quadrupole moment of the metric. As you increase the quadrupole moment, you'll tend to make your shadow more oblate and it'll be elongated in the horizontal direction. As you increase your spin, you're also increasing your frame dragging effect, and that will tend to kind of compress the shadow in the horizontal direction, so it'll be more elongated vertically. Both of these effects cancel out almost perfectly for a Kerr black hole, just because of the symmetries of that black hole. So now that we know what a black hole shadow actually is, we need to understand what is required from your accretion flow so that you can actually observe the black hole shadow. So I took this bulleted list from the 6th EHT paper that was published in April of 2019, and I think it actually summarizes this really well. So first, you need enough photons to illuminate the black hole. You also need the emission to originate close enough to the black hole, but primarily outside of the photon orbit so that it can be gravitationally lensed around it. And finally, you also need the surrounding plasma to be sufficiently transparent at the observed wavelength. So the animation in the top right here is going to hopefully give you an intuitive feel for this first bullet point here. So what you're looking at in this animation, this is what Sag A star might look like if you were to observe it at 1 centimeter radiation. And so what we're going to do as I play the animation is we're going to go from 1 centimeter all the way down to 1.3 millimeters, and you'll see how this big poofy disk will become transparent. And so we picked the wavelength to observe with the EHT based on this third bullet point here. And so the animation at the bottom of the slide is trying to give you a better idea of what you might observe once these 3 bullet points are actually fulfilled. So this is, again, the results of a GRMHD plus radiative transfer simulation, and these are parameters that are reasonable for M87. The first image is just the image at 1.3 millimeters, and the other 2 panels are horizontal and vertical cross-sections of this image. I'm also showing in this vertical dashed line the location of the analytically calculated black hole shadow. And so even though you're going to see a lot of variability, hopefully you can see that there's very frequently a significant peak right at the edge of this black hole shadow. And more importantly, if you were to observe most of these images with the EHT, what you would find is a relatively thin ring of emission, and the ring of emission would be very close to the location of the analytically calculated black hole shadow. So why is it that we have this peak that's very close to the black hole shadow once those free bullet points are actually fulfilled? So this is, again, yet another animation of a simulation. You're now observers that are at the bottom of the screen here. So at infinity at the bottom, you're looking at this black hole. The red circle is the horizon. The blue is the photon orbit. And this line down here, this is the photon path. What I'm going to do is, instead of just sending one photon, we're going to send a packet of photons at different locations along the observer's plane. And we're going to see how this packet of photons will be lensed by the black hole. And so as you can see, this packet of photons is going to essentially fan out when it's really close to the photon orbit, and it'll essentially be probing a really large area of the accretion flow. So here I have highlighted 3 different example packets. So all of these red photons are just going to fall right into the black hole. And if you remember from the free bullet points in the previous slide, we're going to have most of our emission at 1.3 millimeters is going to originate fairly close to the black hole, but outside of this blue ring. And so the way that you should be thinking about this is that we're essentially simulating these photons backwards in time from the plane of the observer. And as these photons move through their trajectories, they're going to be essentially collecting emission when they pass through regions of the accretion flow that have a lot of emission. So these red photons are going to be collecting emission around here. So there will be some emission, but not that much. And the green ones are also going to be collecting emission when they're in this general region, but still not that much emission for these green photons. And it does fan out a little bit, but not too much. The photons that are right at the edge of the photon ring here, which is right at the edge of the black hole shadow on the observer's plane, which is about 5.2, these photons are going to fan out over a really large portion of the accretion flow, and they're going to be collecting a lot of emission throughout this whole region, which is why we expect to see a peak of emission close to the edge of the black hole shadow once those free bullet points are met. Okay, so everybody has, of course, seen this image hundreds of times, especially in this group, but I just wanted to be very clear about what aspects of this image we're actually using for this test of gravity. So we do require that there is a flux depression, which is something that we're very confident about in these images. We're also going to be measuring the radius of this ring and the width of the ring. And so we do that using feature extraction algorithms in the image domain. And one thing that's really important to keep in mind is that what we're actually doing here is that we're measuring the peak of emission along the ring, and we're going to use that as a proxy for the location of the black hole shadow. So there is obviously some uncertainty inherent in this technique. And what we did was we simulated a large number of observations using GRMHD simulations and calibrated for the systematic error that we would get by using this proxy. And so in addition to the feature extraction in the Fourier-domain, in the image domain, we also performed Fourier-domain model fits. So in this case, we're fitting geometric crescent models to the interferometric data. And again, we're measuring the radius of the ring, the width of the ring, and again, we calibrated this with simulated observations as well. And so then we can compare the results that we get from both of these methods to previous mass measurements for M87. And so in red here, this is the measurement using gas dynamics. The blue is the measurement using stellar dynamics. And as you can see, there's a very serious discrepancy between these two. This is actually not that surprising. There are many other black holes that have similar situations, and there are reasons why we might believe the stellar dynamics measurement over the gas dynamics measurement. And so if we compare this to the EHT observations, you can see that both the image domain and the fits with the geometric crescents, which are shown in this magenta curve here, match. And I'm also showing in blue fits using GRMHD images as well. And so what we can do is we can perform a null hypothesis test. And this is what was done in the initial publications from April of 2019. And so what we said in those tests is essentially, is this consistent with a Kerr black hole or not? And what's the size of the error bar on that statement? Kind of how big is the wiggle room that we still have, right? So how different from a Kerr black hole shadow could the black hole shadow be and still be consistent with the EHT measurements and the stellar dynamics result? So the error bar on that is 17%. And this takes into account the uncertainty in the stellar dynamics measurement. It takes into account the uncertainty in the radius measurement, and it takes into account the uncertainty given because of the fact that we're using this proxy to measure the size of the black hole shadow. And so I also just wanted to point out that if we had assumed gas dynamics, we'd be off by a factor of 2, which would tell us that this black hole is not Kerr. We think that this is a very low probability case. And so we're essentially giving it a negligible prior, and I'm going to ignore the gas dynamics measurement for the rest of this talk and just focus on this 17%. So as I've already mentioned, 17% is really not going to do much to constrain the parameter space of Kerr. But what we can do is we can take the Kerr black hole and we can add a perturbation to it. So there are several different parametrized perturbative metrics that have been developed over the years. And what I did in a paper that came out just earlier this year was explore several of these parametrized metrics and try to simulate what the black hole shadow would look like for most of the parameter space for each of these metrics. And so I'm just giving you a couple examples here. So on the left is black hole shadows from the JP metric, that stands for Johansen and Psaltis. And on the right is from the MGBK metric, which stands for Modified Gravity Bumpy Kerr metric. And in each of these panels, I'm just varying one perturbation parameter, and you can see how the size of the black hole shadow depends on this perturbation parameter. And so what we can do is we can measure the radius of the black hole shadow as a function of each of these perturbation parameters, alpha 1 free for JP and gamma 1 2 for MGBK. And we've also changed the spin, which is shown in these different colored lines here. And what's really interesting is that even when you deform away from Kerr, the spin really doesn't seem to have a big effect on the size of your black hole shadow. And so from these plots, you can probably already tell that we'll be able to use the 17% constraint to rule out parts of the parameter space and place a constraint on each of these parameters. But you're probably wondering why you should care. Why is this useful? Why should you care that we can constrain these, random perturbation parameters that you've probably never heard of? So what's really exciting that we were able to do in the paper that was published last week was we were able to connect constraints on these parameters to constraints on the GTT component of the metric, and specifically the 2PN parameter. So in the paper, you can follow this math, and it's actually quite simple. So we first start with the radius for the photon orbit, and we see that it only depends on the GTT component of the metric. The radius of the shadow of the black hole is just the lensed photon orbit, so it also only depends on the GTT component of the metric. If you're wondering, the GTT component of the metric is what really controls the slowing down of clocks, and it's also what you can constrain with, for example, the precession of Mercury around the sun. And so we are sensitive to the GTT component when we measure the size of the black hole shadow. And what we can do is we can then expand the GTT component of the metric. And we did this, first off, it's in aerial coordinates, so it might look a bit different than what you're used to. We've also set G, M, and C to 1 here, but we're doing this expansion in the same way that the PPN expansion is done. And if you're not familiar with PPN, it's post-Newtonian parametric expansion that's used to test gravity. It was developed for the solar system, but it's been used in other tests as well. And so these parameters, this beta, gamma, and zeta parameters, are the PPN parameters. So this term here, this is 1PN, and this term is 2PN. And what we've done in this paper is we've set beta and gamma to be equal to the values that have been measured in the solar system. And this doesn't have to be the case in general. It's possible in non-GR theories that beta and gamma would have different values around the sun than what they would have around a black hole. However, in this case, we're dealing with a situation where we only have one free parameter. We only have one measurement, right? We only measured the size of the black hole shadow. And so we can't constrain free parameters or even more, right? We can't constrain the following orders either, just using one measurement. So what we choose to do is we make the assumption that beta and gamma are equal to the measurements from the solar system. We ignore the higher order terms and we just focus on zeta. And we can do, so this whole term goes away when we do that. We can make the same expansion for the other two parameterized metrics, so the JP metric and the MGBK metric. And what you'll see is that the parameters that we can constrain, alpha 1 free and gamma 1 2, are linearly related to this zeta parameter. So by constraining alpha and gamma, we're really constraining the 2pn terms of these metrics. And so these are the actual constraints that we were able to impose on these parameters. The dashed black line that you see in both of these panels, this is the analytic constraint, which is what I was showing you in the previous plot. Obviously, we made some simplifications in that case. We ignored spin, and it's just a linearized version of the metric. But in these different colored symbols that you see here, this is the full metric, and this is using a full but it's full ray tracing with the full metric, which is how we place these constraints. And we're also showing you how it depends on spin, which is not very much. And the different colors and different symbols are different values for this secondary perturbation parameter for each of these metrics. And so these constraints that we are able to impose on these parameters, if we were to compare this, for example, with what we can do in the solar system, the constraints that we have here are order unity, and this is about 500 times more constraining than what we can do in the solar system. We can also compare this to what can be done with LIGO, and the constraints that we have on the 2pn term are actually quite comparable to what can be done with LIGO, at least so far. And what's really exciting, of course, is that we're observing a completely different area of the parameter space. We're looking at supermassive black holes. They're looking at solar mass black holes. They're also going to be sensitive to the dynamics of the metric, where we are only looking at the metric. Sorry, not the dynamics of the metric, the dynamics of the theory, whereas we are only sensitive to the metric. And so these are
3 minutes. Sorry to interrupt.
Okay, that works out perfectly. And so I just wanted to really quickly in the last couple minutes give you a little bit of a taste for what's to come. So this is, of course, just the very beginning, which I know everybody always says that about these experiments, but I'm going to tell you kind of specifically how we can improve. So we'll obviously have more telescopes. We'll be able to create images with more fidelity. We'll be able to constrain the shape of the black hole shadow even better. But what I wanted to focus on is specifically how we will be able to improve this proxy. What can we do to be more convinced that the thing that we are measuring is actually a gravitational feature and not an astrophysical artifact? So I've hopefully convinced you that we are fairly convinced by that already, but what can we do in the future? So the first thing that we can do is we can look at gradient imaging. So because this is an interferometric experiment, in theory, it's possible to create a gradient image from interferometric data. And if you were to create a gradient image and find a really steep gradient, so this is the same simulation that you've seen earlier. These are the cross sections of it. This bottom row here is the gradient of the top row. And you can see that there's this really sharp gradient right at the edge of the black hole shadow. So if we make a gradient image, we measure the size of the ring, and it's consistent with what we've seen, we'll be even more confident that what we're seeing is a gravitational feature. And I can play this, and you can see that this sharp gradient at the edge of the shadow is fairly consistent. The second thing is variability. So if I take the average of that simulation, this is what that looks like. And so even though there's a lot of variability, you'll have this fairly consistent structures that are right at the edge of the shadow. This is something that we can already start doing. So obviously in the images that were published in 2019, that was over almost a week. And the black hole shadow is about the same size for all of those different observations, which is, makes us a little bit more sure, but obviously 7 days is still a really short time span for M87. So as we continue these observations over several years, this will become much better. The other thing that I wanted to have pointed out earlier is that something that we are not taking into account in when we perform the calibration using the GRMHD simulations is that the GRMHD simulations that we use do not include tilted disks. And there is some work by Chris White, who I know will probably ask me about this, that predicts that the tilted disk would create a ring of emission that is offset from the black hole shadow. So this is also something that maybe one of these free things could help us be more certain about that as well. And the last thing I wanted to point out is that the black hole shadow is expected to be achromatic. And if you remember my title slide, I already alluded to this at the beginning where I showed you this simulation. And you can see that there's this thin, bright white ring that's completely constant while everything else changes around it. And the reason it is white is that it is bright at 3 millimeters, 1.3 millimeters, and 0.87 millimeters, which are the free color images that I'm using for this simulation. And with that, I'll just very quickly go over my summary. And I just wanted to focus on two simple main points here. So first, the first image of M87 can be used to measure the radius of the black hole shadow to 17%. And even though 17% is a pretty significant error bar, it's already really powerful for GR tests. And so the 17% can already constrain the GTT component of the metric at least the 2pn order. Of course, I didn't really talk about orders above 2pn. We've essentially been assuming that they are negligible, but this is something that could potentially, in the future, if we get more data points and so forth, could be used for higher orders as well. So thank you.
Thanks very much, Leah. Nearly silent Zoom clap. Okay. So Dimitri had a question in the chat. Is it possible to infer the inclination angle of the black hole spin axis relative to the line of sight? I guess maybe one motivation is that that is sort of a free parameter, at least in some cases. Or Dimitri, did you want to say it? Or?
Yes. First, thank you very much for the very interesting talk. I greatly enjoyed it and learned a lot from it. But sort of more broadly, so of course, the question about the inclination about the spin axis is perhaps secondary to the question of can you measure the spin? So what is the spin of the black hole? And then, sorry.
Yeah, go ahead.
Then also, how sensitive are the results to the inclination angle?
So I will give kind of two answers to this. So within the information that I've given you here, if you're just using the size and the shape of the black hole shadow, given the 17% error bar, I can actually go back a couple of slides and show you exactly what I mean here. So this plot essentially summarizes all spins and also all inclinations. I forgot to include the legend because the actual plot in the paper has several panels, but the x-axis is showing you the different spins and the different colors are different inclinations. So if you're just looking at the size and the shape of the black hole shadow, the size for all inclinations is still within that 4%, and you're not going to be able to constrain that with just the size and the shape of the black hole shadow. However, what we did in the paper that was published last week was we essentially assumed that the spin axis of the black hole is going to be aligned with the large-scale jet. And so we keep that as, we essentially remove that free parameter and we just assume that the inclination is 17.
So then what is that inclination angle? So if it is aligned, degrees. 17 degrees, okay.
Yeah, so it's almost face on. Yeah. But it is important to note, though, that a completely separate study that's not just focusing on the size and the shape of the black hole shadow was performed in paper 5 from the EHT results. And that's using the fact that we have an asymmetric ring. We have more emission at the bottom. And so you can compare that with GRMHD simulations, and they do have constraints on what the inclination of the spin axis should be given comparing these GRMHD simulations to the fact that we have this emission on the bottom. So it can kind of be done, but not with the black hole shadow.
Thanks.
Yep.
Yeah, whoops, sorry, Andrew, go ahead. I'm sorry, I clicked the wrong button.
Okay. Great talk, Leah. I should probably know the answer to this question, but how much of the error bar in the Newtonian parameter that you get at the end depends on the uncertainty, sort of the a priori uncertainty and the mass? I mean, like, how much would we do better if we were using Sagittarius A, for example?
That's a really good question. To be completely honest, I would just have to do the actual calculations. I can't tell you off the top of my head what would happen to the 17% constraint if hypothetically, if you were to get a very similar set of images for Sag A star and you got the same uncertainty in the radius of the ring for Sag A star. Hypothetically, the fact that we have a much better constraint mass for Sag A star than M87 obviously will affect the 17%, but I can't tell you off the top of my head exactly how much. I haven't actually done that calculation yet, but it should be better. We'll find out soon.
Other questions? Yeah, Chris, please.
Well, you had mentioned tilted disks, but I actually had a question in a different direction, just in terms of things that can, confounding factors in these sorts of measurements. How much does, say, the size of the ring that we see currently with EHT depend on the electron model if you're doing like a GRMHD simulation? And if it does depend on it, can you like flip this around and say, let's assume GR is and everything is spot on. Can we place limits on what electron models make sense, or how hot the electrons have to be at different parts of the accretion flow?
Okay, so I'm going to give essentially two answers to this as well. So the EHT party line is that yes, and this is exactly what we did in paper 5. So there's an entire paper that does exactly this and does try to place constraints on many of the different parameters that we use in these GRMHD simulations. However, sadly, many of these parameters turn out to be a bit degenerate, and because of the variability, it's not that hard to create at least a few snapshots that are broadly consistent with what we see for a relatively large range of parameters. I know that there are other people on this call that were more involved in that particular study, and of course, if you want to speak up and talk about this, please do. The other aspect of this, which I think is relevant for my argument, is the following. So what I didn't really get a chance to talk about too much here, but is, at least for me personally, something that makes me much more confident in what we're doing, is the fact that, especially when you're looking at the geometric crescents, when we fit them to the data, there's significant evidence for the thickness of the ring being less than 20% of the radius. And what happens is that it's actually relatively hard to create something that is constant over the 7 days and is that thin that is not close to the black hole shadow. So that's what kind of, it's that 20% bound that makes me personally more confident on it. But yeah.
And actually, speaking of then of the thickness of the ring, are those, because you said some of this analysis is done in the image plane, are those algorithms public at all? Is there a script the EHT has? So if I have a GRMHD ray traced image, can I just use the same algorithm to get kind of the same measurement of the ring?
Yes, I believe Andrew's on this call. His imaging algorithm is, I believe, publicly available, and I believe there is a script that does just that. Andrew, do you want to comment on this at all?
Yeah, the algorithm for imaging and for getting the width of the ring and the diameter of the ring is all public, though it's not super well documented. So I'm happy to help if you send me an email with any.
I'll look into that.
Cool. Other questions? So we can also, next up before the break is open discussion. So first, let's thank Lia again for the excellent talk.